Hello, welcome to this class of thermoanalytical methods, where we are talking about a simple thing which was the mass loss, and this mass loss we are trying to monitor with respect to temperature increase, and that is very simple and a very straight cut way of knowing the thing, that how much stable the compound is or the material is. So, one important thing is that it is very much useful for material characterization, and also sometime we can use this particular technique if we know nicely at what particular temperature the amount of mass loss is taking place, and that mass loss can be very much useful for some process development also. And so far we have seen that there will be something, that means that you can have the water of crystallizations such as that what we have discussed in case of calcium oxalate, that two of the water molecules which is present in the crystal lattice and nicely networked in terms of hydrogen bonding or trapping inside the void of the crystal lattice, what we find that the removal of these things will accompany the weight loss or the mass loss, such that we can have the corresponding dehydrated sample. So, after knowing this thing, that means the dehydration process can take place, and if we have more number of water molecules, say 5, 6, 7 up to 10 water molecules, we have seen the examples of sodium carbonate. So, at the same time, if we see that if something is happening, such as we have seen in the case of heating FeS2. So, what is happening when we go for heating this particular FeS2 species? Because we know now very well that if there is a loss, that means the loss of this thing, or we have seen that in case of your magnesium oxalate or calcium oxalate, the gases which are evolved. So, these gases, these are carbon monoxide or carbon dioxide, and that basically give birth of a typical another analytical technique related to mass loss as well as the temperature change for these species. So, which can be termed as evolved gas, what we can consider. So, what gases which are coming out from these samples, that means the degradation of your oxalate species or the carbonates. So, we can study nicely the degradation of oxalates, number 2 carbonates or any other species. Even sometime we can go for the corresponding degradation of nitrates, etc. But in other cases, when we see that this evolved gas, if we go for its corresponding analysis, it can be termed as the evolved gas analysis. So, evolved gas analysis, and we have also seen the two different types of this particular type of mass loss when we consider the typical environment. So, when gases are coming out, such as your carbon monoxide or carbon dioxide, which are coming out from the solid thing which we are heating. So, this thing will go, and these two gases which are coming out, so above the solid we have this particular gas. So, these two gases basically can maintain the corresponding environment. Similarly, when we heat something, that means we heat this in presence of O2 or in presence of air, we all know that we are looking for something where some high temperature reaction can be feasible, such that you can have the corresponding iron based sulfate formation, that the sulfur is getting oxidized. So, when sulfur, which is present as the anionic form of this metal ion salt, is getting oxidized, so degradation of any other non-metallic species like the sulfur burning, phosphorus burning, nitrogen burning, the gas burning also, the nitrogen gas burning. So, we can consider one after another for their typical burning process. So, in this particular burning process, if we consider that something is happening, and ultimately what we have seen that it goes ultimately to the corresponding oxide formation, that means Fe2O3 formation from this iron. So, quantitatively what we can do is that quantitatively the amount of iron which were present in this unknown sample. So, any other sample containing these metal ion species can be converted to its corresponding metal oxides. And sometimes if we are able to make or able to produce or able to prepare these metal ion oxides or metal oxides, because originally these are present in some oxidation state of +2 or +3. So, metal oxides or metal ion oxides, we can produce their fine particles. So, it is possible to prepare those fine particles, and if they are in the very small size area or the nanometer area, we can consider that we will be able to prepare corresponding nanoparticles which have very good application, tremendous application in terms of their other property, other physical property. If they have corresponding semiconducting behavior, we can use these particles as the semiconducting material in the sensor process or any other thing. So, in between, after getting this, in between, when we see that we are talking about the corresponding burning of the sulfur part or the sulfide part or H2 minus part, which is present with this iron in the ferrous state, iron is in the ferrous state. So, the corresponding conversion of the sulfate, and if we consider simply the molecular weight of the sample what has been taken to that of the molecular weight of the species what is being formed due to the oxidation by O2, we see that in this particular step there will be some weight gain at high temperature heating. So, we will see this particular example that not only we have the weight loss or mass loss in some cases, but we can have something where we can see the corresponding weight gain also. So, this particular technique, the thermogravimetric analysis and its corresponding derivative one, the derivative thermogravimetry, can also be very much useful to monitor, to identify and to check the corresponding amount of weight gain. So, nicely we can monitor the weight gain process. So, that we will see that how we can have and how much you have the corresponding weight gain. So, what we see here that the example of some chemical reaction what we can have with an increase in mass, that means we can have this particular one, that this particular reaction which is a thermochemical reaction we will consider. So, any such reaction when heat is utilized for any transformation, it can be decomposition or it can be conversion related to that of our oxidation with an increase in mass. So, like that of our FeS2 burning in air is similar to that, we have a corresponding increase in mass. So, instead of taking your FeS2 sample, we can also take a typical example again taken from your book. So, that oxidation of iron, we are taking that oxidation of iron powder in air. So, what we have seen just now that we are talking something related to semiconducting oxide material. Your FeST is your oxide material, but if your environment is such that Fe2O3 can be converted to very fine iron, metallic iron powder. So, what we should do? We should do something that at high temperature, so at high temperature we can go for its reaction with hydrogen gas or any other source where this H2 can go for the typical reduction reaction. So, after that reduction, that means we start from here, we have the sulfate as the intermediate, then we go to the corresponding oxides and some of the time we can also get the other variety, that means Fe3O4, the mixed oxide of the iron can also be able to make from there, and the fine particles of Fe2O3 is also there, and if we go for the corresponding reduction of this Fe2O3, we can go for fine iron powder. So, now we just try to monitor the corresponding these iron particles, because these iron particles can also again be your fine particles. You can function these as the nanoparticles, but again in terms of say simple characterization, how good they are, because sometimes these particles, if they are very fine, they immediately react with the O2 present in airs, and these fine particles will be pyrophoric in nature. So, they can be pyrophoric, they can be catalytic, and they can have other good examples. So, taking this particular information, what we have seen previously also in terms of your carbon powders, the carbon particles, the carbon powder, when we burn in presence of nitrogen and in presence of oxygen, we see that the complete burning of carbon as carbon monoxide as well as carbon dioxide is only possible when the environment is your O2 environment. But when the environment is nitrogen, we will not be able to go for its corresponding oxidation. So, your oxidation will not take place when your nitrogen is there, but in case of O2, this oxidation is possible to happen. So, if you get these fine iron powder particles there, if they are so pyrophoric that even at the room temperature, when it is exposed to your O2, it can immediately react. So, in air or O2 environment, if we go for the corresponding oxidation of iron in air, so this is a typical characterization process, and how the corresponding mass gain profile or mass gain plot can be available to us, that we can see from the corresponding TGA plot. That means, what we see that in a case of your oxidation of iron in air, so we have taken roughly about 23 milligram of this particular sample, and we go for the corresponding heating of the sample on some alumina pan. So, this particular part we just see that how much we get, that is the corresponding to, that means this particular change. So, this wet loss basically we are considering it from almost this is almost this particular percentage, that means you have this 100% of the sample. So, what weight we have taken? We have taken 23.7141 milligram. You see such a sensitive balance we use, thus that we can take the weight up to 4th place of decimal. So, this 4th place of decimal will immediately tell us that if we heat the sample at say 550 degrees centigrade or 600 degrees centigrade or 700 degrees centigrade, we have a continuous mass gain for this particular sample, and which is complete around say 950 degrees centigrade. So, at 950 degrees centigrade we have a corresponding weight gain which is almost 140%. So, 100% was your iron powder, and by taking its corresponding oxygen, it is converted to your oxide. So, iron oxide what is formed, which is more than that, that means weight gain is up to 40%. So, this particular step, that means considering this point which is above 1000. So, above 1000 degree temperature, so about 1040 or 50 degrees centigrade, we see that the gain is about 40%. So, your mass which was originally 100% with regard to your 23.7141 milligram of your iron powder is gaining a weight of 9.4863 milligrams. So, this particular weight will also tell you what is forming over here. That means, the corresponding composition of the oxide we know, and this composition of oxide will immediately tell us that whether your species is forming what we have seen just now, that whether it is Fe2O3 or Fe3O4 for this particular process, because the weight of iron is known and the weight of the corresponding oxide is known and the percentage gain is also known. So, this particular thermogravimetric analysis is a very useful one. What we know due to the corresponding mass conservation and the mass gain for a particular process. And we have seen a particular type of the corresponding SDTA technique, that if we go for the corresponding derivative one, and this derivative one is not also very much monotonous, that means if we go and if we supply such an air passage, that means 50 milliliter of air per minute is passed on the sample and we heat the sample, and the derivative plot is actually giving rise to the corresponding change of this temperature. So, it is the corresponding temperature change for this derivative one is a 5 degree centigrade, and this temperature change with respect to the corresponding temperature for the sample is giving you a derivative plot. And when we do not go for, that means we have variable temperature rise depending upon your rate of mass loss, because when the mass loss is more, the furnace temperature change should be slowed down and we get a typical plot of this type. So, as a result, what information we get, that information will tell us that we cannot restrict the thing to Fe2O3 only. We can also have the Fe3O4, because this is only the corresponding one for the oxidation of complete oxidation, that means in the ferric form. Fe2O3 is the ferric oxide, but this we consider as Fe3O4 is a ferrosoferric oxide. So, ferrosoferric oxide means you can have certain percentage in the ratio of 2:1. Two of the iron centers are present in the trivalent state, that means in the ferric state, and one will be in the ferrous state. So, this is in the lower range, that means this will form first, and when you have the complete oxidation, the Fe3O4 will be converted to Fe2O3. So, this 40% weight gain at this particular time, that means around say 800 to 900 and up to 1000 degree centigrade, is due to the formation of both. And what we can find, that if we know the typical formula of this thing, we can find out from this particular transformation the amount of Fe2O3 and amount of Fe3O4 formation. In this particular plot, that the derivative plot is also showing, because we will see now in this particular class or in the next class that what is known as the corresponding differential thermal analysis. And we can have for this particular thing, that means whether we have a typically plot of upward in the upward direction or in the downward direction, what we see that this particular weight gain process is also a exothermic process. So, oxidation, and most of these oxidations are giving rise to the corresponding temperature rise of the sample. So, we have a corresponding temperature rise of the corresponding sample what is heated. So, is a typically exothermic reaction. So, most of the oxidations are considered as they are very much exothermic in nature. So, how we use the corresponding data what we get, that means the at what temperature we have the corresponding change in the corresponding mass, and such that we can have different data points. So, temperature versus mass of the sample we plot, and now we try to evaluate the informations what we can gather, which is quantitative in nature, is known as the corresponding quantitative evaluation of your data what we can get from your thermogravimetric analysis. So, we can have different steps, and those steps can be considered, can be evaluated as a change in mass before and after the effect. So, the corresponding baseline is horizontal. So, that we are seeing from the very first day of this thermometric analysis, that if we can have a mass loss like this, and we know that one is the corresponding temperature axis and the other is your corresponding mass loss axis, and we see that this particular magnitude of this is the corresponding mass loss. So, we see that this particular one is also a horizontal plot and this is also a horizontal plot. So, when we start, basically we consider that our weight loss is taking place from a baseline. That means, from a temperature range of say this to this, where we see that the water of crystallizations are going out in case of heating your oxalate samples of calcium and magnesium, and this water loss from this particular point is that within a very small temperature range, this range is very small. So, within a very small temperature range, our elimination of water from the crystal lattice is taking place. So, before that, that means this is the room temperature starting, and this can be around 100 degrees centigrade. So, if your room temperature is 28 degrees centigrade or 30 degrees centigrade, so within this range from 28 to 100 degrees centigrade, we have a typical baseline. And when the mass loss is completed also, say around 140 or 145 degrees centigrade, if we consider it, and after that your line is again horizontal. So, this is baseline for the first weight loss or the first mass loss step. Then the second one, where this particular range is also a typical baseline. So, this can also be considered as another baseline for the second step, if it is there at all, second step of your mass loss or weight loss in this particular fashion. So, the quantitative data, that means if we get a very sharp change, that means is almost a very small temperature range. So, this is also a very small temperature range, but instead of this, if we have a process like this or a process like this for these two steps, that means a continuous one, not a very discrete steps, is very difficult to find out up to what particular temperature you have the corresponding baseline, because it is continuously degrading. So, in that particular case, the delta m value for the removal of water of crystallization is very difficult to identify. So, the very important criteria what we should have for the quantitative analysis of the DTA data is that you should have a typical baseline at the beginning and at the end, such that in a very small temperature change window we have a typical delta m value, and within this particular range from this axis we found out the m value, delta m value in milligram, such that we can find out this, and we should try to correlate it that whether this mass loss will correspond to the corresponding amount of water which is being lost from the sample taken for your analysis. So, this baseline thing, that means we should have, so before and after we should have the baseline, and which should be horizontal in nature. Then what we can do that the content or check the stoichiometry of the reaction using pure starting material. So, sometime whatever precipitate we can have, as I told you that in case of your precipitation of your calcium oxalate or magnesium oxalate, externally we add oxalate salts as the sodium salts, and we add all these to the corresponding beaker, and we get the corresponding precipitate of these as the corresponding precipitate of calcium oxalate or magnesium oxalate. But remember at that particular point or at that particular time that in case of your pure calcium present in the sample or pure magnesium present in the sample, we get quantitatively the corresponding amount of your oxalates, but the real samples are not so pure. We have certain percentages of calcium as well as certain percentages of magnesium present in it, but there are other extraneous samples. It can be your other bivalent metal ions, and those bivalent metal ions can give or may not give also the corresponding oxalates at the insoluble precipitates, but if they give the corresponding oxalates at the precipitates, so your precipitate what you are expecting to be of calcium oxalate is further contaminated with that of other bivalent metal ion oxalate. So, how we check this particular plot for your quantitative thing, that means the real plot for any weight loss process, we should have the pure sample of or certified sample of your calcium oxalate or magnesium oxalate. We take that particular sample and heat that, and we take the corresponding weight loss at those particular temperatures. So, this basically is taken from your the one good book is Principles and Applications of Thermal Analysis by Paul Gabott, and we have adapted some of these things, that means the plots and all this from this particular book. So, if we take now a very simple example what we are studying from our school days, that a good reference you can have for handling your instruments is copper sulfate, which is having 5 water of crystallizations. So, copper sulfate pentahydrate we call these. So, this copper sulfate pentahydrate, what we find, and we try to see the copper environment, whether your these water molecules are bound to it, or we can have some sulfate bound to it, and all these things, how sulfate. So, two things, that means you have the anionic SO4 2 minus and the water molecules which are surrounding your bivalent copper 2 center, and in the solid state packing, basically solid state crystal you have, and the packing is therefore very important. And when it is packed, basically we are packing this particular hydrate salts within the crystal lattice, and when we heat it, and what we are looking for, the corresponding loss of water of crystallization. So, here also we are looking for this loss, as well as we will be looking for something where we can consider that whether your sulfate is also getting lost from the species or not, that we will also see, because we have a very good example. Always we should try to keep in our mind that when we heat it, we get the corresponding sulfate of it, and then we can get two things together. That means, we can have the corresponding oxides, or we can have the corresponding pure metal, that means the iron powder. So, these are the things basically what we can consider. So, heating a particular sample, which can be a very good reference material for any instrumental thing which can be standardized. So, it is your reference material also for standardizing the instrument, for standardization of TG apparatus. So, if we want to standardize the corresponding TG apparatus, we must take a very pure sample of your the copper sulfate pentahydrate. So, if we take about 31.5 milligram of this particular sample, what we find that this 31.5 milligram of this sample, if we heat it, so we have one step of loss, then the second step of loss, and the third step of loss. Then we have a very big loss, and then we have the corresponding residue. So, this basically tells us the typical quantitative analysis of your TG plot, and this quantitative analysis of this TG plot will give us the corresponding information that in a stepwise manner, because we know that these steps, if we find, if your eyes are very well trained, and you know that this is a very good baseline, but here to detect this particular baseline is very difficult sometime. So, if it is difficult, we should go for the corresponding derivative plot, otherwise we have this, and then again we have a very broad or a very long baseline. So, look at these things, that means this is the axis for your weight loss, that means the 10 milligram scale. So, this is the 10 milligram scale. So, these steps, that means the step 1 is not even 10 milligram, it is close to 5 milligram, it is 4.5 milligram. Second one is also that, third one is still less, but the fourth one is a very big one. So, which is 10 milligram, 10.1187 milligram weight loss, and ultimately we have the residue. And most of the time what we have, because we are ending over here where the temperature we have reached is 1000 degree centigrade. So, this 1000 degree centigrade temperature will tell us that what is your corresponding residue, what remains there. So, analyzing these things, that whatever sample you have, if you know that a pure sample of copper sulfate pentahydrate is given to you, and what I just told you, that we can have the corresponding weight losses, these weight losses. So, these two, that means the loss of sulfate as well as the loss of water molecule, can be your choice, and what are the corresponding residue, that also we should think. So, if we think for a while before we go for the next class, that we should have some residue, because is that the percentage of this residue if we are able to determine, because the detailed analysis of this TGA plot will tell us what should be your residue and what should be the corresponding mass loss in steps. That means, different steps you have. So, if you consider that you have 5 water molecules and 1 sulfate anion, so 5 plus 6 species are there. So, we may not get 6 steps for this water loss, but we can have less number of those steps, but meaningfully and chemically meaningful also, because we must have something which is your residue, which should have a good formula for that, the way we have seen in case of your heating of your FeS2 or your heating of your iron powder to get the corresponding oxides of your iron. So, in our next class we will see how we can analyze and how we can quantify basically the corresponding thermal degradation of pure copper sulfate pentahydrate sample. Okay, thank you very much.